A fan can meet its catalog curve on a test stand and still disappoint after installation. The missing piece is often system effect, extra loss or distorted flow created by the way air reaches and leaves the fan. It does not mean the fan is defective, and it is not a universal penalty. The exact result depends on geometry, operating point, air density, pressure basis, and the complete connected system. Start by separating two boundaries. A standardized fan test controls the inlet, outlet, measurement planes, and air conditions. The installed unit may add filters, coils, dampers, screens, plenums, elbows, transitions, and access panels. The fan curve describes the tested fan arrangement. The installed operating point is where that fan and the real system interact. At the inlet, obstruction reduces effective area and raises local velocity. A nearby wall, filter frame, structural rail, cable tray, or partly closed damper can pull more flow through one side of the opening. The average airflow may look acceptable while the wheel receives a lopsided velocity profile. That non-uniform approach changes blade incidence and can increase loss, sound, and vibration. A nearby inlet elbow adds another problem. Flow at the outer radius can arrive faster than flow at the inner radius, and the bend may introduce swirl. The wheel then sees different velocity and angle around its circumference. A turning vane or larger plenum may help in a specific layout, but there is no universal elbow distance or straight-duct multiplier that guarantees uniform inflow. Clearance is therefore an aerodynamic question, not a single-dimensional rule. The useful space depends on fan diameter, inlet shape, area ratio, obstruction solidity, upstream velocity, bend radius, and available pressure. Review the actual velocity field at the fan plane, not just the distance shown on a plan. Physical access and service clearance do not automatically equal aerodynamic clearance. The discharge side can create system effect too. Centrifugal and axial fans can leave the outlet with non-uniform velocity and residual swirl. A tight elbow attached directly to the discharge can load one side of the flow and convert useful pressure into mixing loss. The direction of the elbow relative to wheel rotation or outlet profile can matter, but the consequence must be checked for the exact fan and layout. Abrupt transitions are another common loss mechanism. A sudden expansion can separate from the wall, while a sharp contraction accelerates the flow and adds turbulence. Poor alignment between the fan outlet, flexible connector, duct, silencer, coil, or heat exchanger can create recirculation pockets. A smooth-looking three-dimensional model still needs area ratios, angles, surface details, and operating points to be evaluated. On a system curve, these added losses act like more resistance. The intersection with the fan curve can move toward lower flow, and efficiency or absorbed power can change with it. Increasing speed may recover airflow, but it can also raise sound, power, and stress. A speed increase is not proof that the root cause was solved. First, identify which loss belongs to the fan, the system, or the measurement method. Diagnose with measurements that preserve the boundary. Confirm rotation, speed, voltage, control command, air density, filter condition, damper position, and pressure tap locations. Measure a traverse where the method is valid, compare static and total pressure consistently, and check current, power, sound, and vibration. Smoke, ribbons, multi-point velocity probes, or validated simulation can reveal non-uniformity in swirl. The AHU project photograph shows multiple plug fans inside a real air handling enclosure. It establishes the physical proximity of fan openings, compartments, coils, panels, and service space. The fan wall and retrofit images illustrate different flow-out concepts. None of these images measures a system effect loss or proves that one arrangement is superior without matched test data. Correction should follow the evidence. Remove unintended blockage first. Open or relocate a damper if its verified function allows it. Improve inlet area, plenum depth, bend radius, turning guidance, outlet transition, or component alignment where measurements identify the problem. Then retest the same duty definition. Do not change several variables at once and call the last change the cure. The defensible conclusion is simple. System effect is the difference between a tested fan boundary and the flow conditions created by the installed system. Protect the inlet profile, manage discharge swirl and transitions, and commission the combined fan system operating point. record geometry, controls, air conditions, pressure basis, measurement planes, and acceptance limits so the result can be repeated.